We are swimming in an ocean of energy, an endless sea of potential that surrounds us every day. It pours down from the sun, bathing our planet in light and warmth, a gift from the cosmos that we often take for granted. This energy, known as solar energy, has the potential to power our world many times over, offering a clean and sustainable alternative to fossil fuels. Imagine for a moment the sheer scale of the sun, a star radiating energy in all directions, a colossal furnace burning at millions of degrees. Now, consider this. Earth receives only a tiny fraction of that energy, a mere sliver of the sun's immense output. Yet, this fraction is still enormous, more than enough to meet all our energy needs if we can harness it effectively. Every hour, enough sunlight reaches Earth to satisfy global energy needs for an entire year, a staggering amount of power waiting to be tapped. This abundance makes solar energy one of the most promising renewable energy sources at our disposal, a beacon of hope in our quest for sustainability. Unlike fossil fuels, it is inexhaustible and readily available as long as the sun continues to shine, providing a reliable and constant source of energy. The challenge lies in capturing this energy and converting it into a usable form, a task that requires innovation and technology. This is where solar panels come in, the silent sentinels of the renewable energy revolution. These marvels of engineering harness the power of the sun, transforming sunlight into electricity through a process that is both elegant and efficient. This process, known as the photovoltaic effect, is the key to unlocking the potential of solar energy, a crucial step towards a sustainable future. Solar panels, those sleek, rectangular structures often seen on rooftops, are more than just modern architectural additions. They are essentially collections of smaller units called solar cells, which are the true powerhouses behind solar energy. These cells are the workhorses of solar energy conversion, tirelessly converting sunlight into usable electricity. They are made primarily of silicon, the second most abundant element on Earth, found in sand and rocks. Silicon's abundance makes it an ideal material for mass production. Silicon is a semiconductor, meaning it has electrical conductivity between that of a conductor, like copper, and an insulator, like glass. This property is crucial for its role in solar cells. This unique property allows silicon to interact with light in a special way, enabling the conversion of sunlight into electrical energy. When sunlight strikes a solar cell, it sets off a chain reaction that generates electricity. This process is known as the photovoltaic effect. The secret to this process lies in the structure of the solar cell. Each cell is meticulously designed to maximize efficiency. It's a sandwich of sorts, with two layers of silicon treated to have different electrical properties. These layers create a junction that is essential for the generation of electricity. This creates an electric field within the cell, ready to harness the energy from sunlight. The electric field acts as a catalyst, driving the movement of electrons and generating a flow of electricity. The two layers of silicon in a solar cell are not identical. One layer, known as the N-type, has extra electrons, while the other, the P-type, has spaces for electrons called holes. This difference is crucial for creating the electric field. When the N-type and P-type silicon come into contact, a curious thing happens. Electrons from the N-type layer rush to fill the holes in the P-type layer. This creates a region in the middle, called the PN junction, where an electric field exists. This electric field acts like an invisible gatekeeper, directing the flow of electrical charge. It's this flow of charge, driven by the sun's energy, that we harness as electricity. Sunlight is more than just light. It's a stream of energy packets called photons. When these photons strike the solar cell, they transfer their energy to the electrons in the silicon atoms. With enough energy, an electron can break free from its atom, becoming a free electron. This leaves behind a hole, and both the electron and the hole can move within the silicon lattice. Remember the electric field at the PN junction? This field acts on the free electrons and holes, directing them in opposite directions. This separation of charges creates a potential difference, like that between the positive and negative terminals of a battery. Section 5. The power of one individual cells and collective strength. Each solar cell on its own generates a small amount of electricity, typically around 0.5 volts. To power our homes and cities, we need much higher voltages. This is where the concept of modules comes in. Multiple solar cells are connected in series like links in a chain to increase the voltage. These interconnected cells form a solar module, typically producing around 12 volts. These modules can then be connected together in parallel to increase the current or the amount of electricity flowing. This modular design allows for scalability from small rooftop systems to vast solar farms. Section 6. The long game durability and efficiency of solar panels. Solar panels are remarkably durable. They have no moving parts, reducing the chances of mechanical failure. With proper maintenance, solar panels can last for decades, providing clean energy year after year. The efficiency of solar panels, or how much sunlight they can convert into electricity, has also been steadily increasing. Current commercial solar panels have efficiencies ranging from 15% to 20%, meaning they can convert that percentage of sunlight into usable electricity. However, there's still room for improvement. Research is ongoing to develop even more efficient solar cells using new materials and designs. Some experimental solar cells have already achieved efficiencies of over 40%, pushing the boundaries of solar technology. Section 7. The storage conundrum, addressing solar energy's intermittency. One of the significant challenges of solar energy is its intermittency. Unlike traditional energy sources, solar power is dependent on weather conditions and the time of day. The sun doesn't shine constantly, and solar panels can't generate electricity at night. This variability can lead to periods where energy production is insufficient to meet demand. This means that we need efficient ways to store the energy generated during the day for use when the sun is down. Without proper storage solutions, the reliability of solar energy is compromised. Battery technology is advancing rapidly, with new types of batteries offering higher storage capacity and longer lifespans. Innovations in lithium-ion and solid-state batteries are particularly promising. These batteries can store excess solar energy generated during the day, releasing it at night or during periods of low sunlight. This ensures a more consistent and reliable energy supply. Another approach is pumped hydro storage, where excess solar energy is used to pump water uphill to a reservoir. This method leverages gravitational potential energy. When energy is needed, the water flows back down, generating electricity through a turbine. This method is highly efficient and can store large amounts of energy for extended periods. Section 8. Land of Opportunity, balancing solar farms and our ecosystem. As we transition to a more sustainable energy future, we need to consider the land requirements for large-scale solar energy deployment. While it's true that solar farms require significant land area, the potential impact can be mitigated through careful planning and innovative solutions. One promising avenue is the development of floating solar farms. These installations are built on bodies of water such as reservoirs or lakes, minimizing land use conflicts. Additionally, solar farms can coexist with agriculture. Agrivoltaics, the practice of integrating solar panels with crops, allows for dual use of land. Crops can benefit from the shade provided by the panels while the panels generate clean energy. Section 9. A brighter future, solar energy for a sustainable world. Solar energy has the potential to transform our world, providing clean, abundant power to communities worldwide. It offers a pathway to reduce our reliance on fossil fuels, mitigating climate change and improving air quality. Moreover, solar energy can bring electricity to remote and underserved communities, improving living standards and fostering economic development. Off-grid solar systems with their own panels and batteries can provide reliable power in areas without access to a central grid. As we look to the future, solar energy will play an increasingly important role in our energy mix. Continued innovation, coupled with supportive policies and public awareness, will pave the way for a brighter, more sustainable future powered by the sun. If you enjoyed this video, don't forget to like and subscribe for more content on sustainable energy solutions.